Welcome to this module of runaway reaction or reaction and runaway problems, because these runaway problems are more critical in chemical process safety. So we thought that we must give you an overview about those reaction runaways and scale up aspect. So in this particular module, we are going to discuss certain fundamental principles, those who are related to the reaction runaway. We will discuss about the causes of various kind of over pressurization. We will discuss about the basic concept of heat of a reaction, then adiabatic temperature rise, Arrhenius relationship, and we will discuss about the thermal runaway aspects, then phi factor, heat losses, changes with the time of scale. Then we will discuss about the reagent accumulation and onset temperature related to the exothermic aspects, and we will discuss about certain safety factors for thermal hazard data. So let us have a look about the hazards, those who are arising from the pressure. So while we consider the reaction hazard, the temperature is rarely a hazard on its own. Although sometimes when it is within the domain, within the controllable domain, then temperature never put forward any kind of hazard. So the impact of any temperature rise, sometimes these temperature rise may take place because of certain conditions like exothermicity or cooling temperature failures, etc. So the impact of any kind of temperature rise on the system is much more important, because this may lead to the other catastrophic problems. So there are three potential sources of overpressure. One is the gas generation from the normal processes, and this took place in the Bhopal gas tragedy when because of the high temperature, the CO2 built up inside the MIC tank while reacted with the water, and it created a lot of problem, and all the safety processes, they were failed. The second aspect is the vapor pressure effect as a consequence of heat from the normal processes. The third one is the heat from the normal process leading to the secondary reaction at elevated temperature, that is gas or a vapor pressure effect, in other words you can say. Now let us have a look about the vapor pressure effect. Now this vapor pressure effect is attributed to the Antony theory, and this theory you can look in the chemical engineering thermodynamics aspect. So this vapor pressure effect is attributed to the Antony plot. Now this plot is attributed to the Antony equation. So the Antony equation is a class of semi-empirical correlation describing the relation between the vapor pressure and a temperature for pure component. Now why there is a need of this plot or this relationship, because in the previous slides we have discussed that sometimes the temperature may lead to, because temperature sometimes is a safer limit, but this temperature may create the problem of overpressure. So whenever we are talking about the relationship between the temperature and pressure, then we must have a certain correlations. So Antony equation, this provides the solution for this particular aspect. Now this Antony equation is derived from the Clausius-Clapeyron relations, and it can be derived by from the sealed cell data. So this is the Antony plot. Log of minus log of pressure to the base E is equal to A plus B upon C plus T, that is the T is the temperature. So for a vapor pressure system, the log pressure log P to the base E is directly proportional to the 1 upon T. So by this way you can plot this logarithmic plot with the pressure versus 1 by T. Now if we recall, if we have a gas generation system, then Ln pressure is equal to 1 plus B upon C plus temperature plus tau. Now where tau is a factor that is due to the generation of permanent gas, and in that particular case this log Ln pressure is not directly proportional to 1 upon T, and you may see that the the nature of the plot would be like this. Let us have a look about the heat of a reaction. This is a very common phenomena, so we will not devote much time towards this particular aspect, because in chemical engineering thermodynamics or engineering thermodynamics we have gone through this heat of a reaction aspect, usually represented by delta HR, and it is having the unit of kilojoule per mole. So let us see that for a reaction A plus B, this gives the product, say maybe C. So the heat of a reaction is the quantity of a heat released or absorbed as a product are formed. So there are two types of heat of a reaction. One is exothermic, when the heat is released, and the second is the endothermic, when heat is absorbed by the system. Now you can see there in this particular slide we have listed some reference heat of a reaction, like acid or base neutralization may have an exothermicity of 60 kilojoule per mole. Then esterification of a methanol or acetic anhydride is having the exothermic heat of reaction 67 kilojoule per mole. Then hydrolysis may have a heat of reaction of minus 97 kilojoule per mole. Diazotization, that is the substituted amine hydrochloride, having the heat of reaction in the range of say minus 117 kilojoule per mole. Then methylation, that is, this may have a heat of reaction of minus 104 kilojoule per mole. And Grignard reaction, it may have a heat of a reaction minus 200 kilojoule per mole. Now the standard heat of a reaction you can have from various handbooks. Now let us have a look about the adiabatic temperature rise. So the total temperature rise in the reacting system due to exothermic activities were there no heat loss to the surrounding, and it is given by delta T adiabatic is equal to delta HR into N upon MCP5. Now here N is the number of moles of a reactant, Cp is the heat capacity having the units of joule, kilogram inverse and Kelvin inverse. Delta HR is having the heat of a reaction, M is the mass in the reactor, which is in having the unit of kilogram, and phi factor, we will explain this in the subsequent slides later on. Another aspect is the reaction rate. This is attributed to the Arrhenius relationship, and which is represented as K is equal to A e to the power minus E upon RT, where K is the rate constant, A is the frequency factor, E is the activation energy, R is the rate of heat production is depend on the reaction rate. For the pseudo first order by dQ upon dt is equal to K delta HR to M. Now this dQ dt is the rate of heat production. Now this K is the rate constant having the first order, and M is the quantity of a reagent available at time t. Now let us have a brief look about the reaction kinetics, and you must not confuse about the delta HR and EA. They have the same units. So delta HR, that is the heat of a reaction, is the overall energy change during a process. So high delta HR, that is the heat of reaction, a lot of energy change, and a low heat of a reaction, then a small amount of energy change may take place. So low EA is the energy required to initiate the change. So if we are having the low EA, that is facile reaction occur at a lower temperature or pressure, and if you are having the high EA, that is a difficult reaction only occurs at a higher temperature or pressure. So these are the certain suggestive measures for the reaction kinetics. Let us have a discussion about the kinetics of heat release or sometimes loss. The heat release rate, that is from an exothermic reaction, increases exponentially with the temperature. So this is a very, you can say, the catchy line, so that you can analyze that if any kind of catastrophe may take place, then how we can analyze that how much quantum of the heat release from the kinetic studies. Now heat loss rate, now from a chemical reactor increases linearly with the temperature with this formula dQ by dt is equal to UA delta T, where U is the heat transfer coefficient having the unit of watt meters to the power minus 2 Kelvin inverse, and A is the heat transfer area usually represented in square meter, and delta T the temperature difference between contents and a jacket. So delta T is important. Sometimes you may experience the thermal runaway problems, and as we have discussed, the governing equation is this one. Now, here the dq by dt is on the y-axis and the temperature on the x-axis. So you need to find out that what is the critical temperature over which there may be chances of thermal runaway reaction. So in case if by any means if there is any exothermic process and excess heat being liberated, then you need to find out that how much quantity of heat removal is required for cooling, so that it may work below this critical temperature radiation. Now, since if by any means it goes beyond this critical temperature range, then there may be a chance of thermal runaway, and you need to take the appropriate safety measures to overcome such kind of scenario. In past, there are several reactions that took place because of this thermal runaway aspect. Now remember, a thermal runaway is the progressive production of heat from a chemical process and occurs when the rate of heat production exceeds the rate of heat removal. So that means certain imbalance took place between the cooling aspect and the heat production aspect, because the exothermicity is known. So you can analyze this scenario and you can take the appropriate measures to control this particular catastrophic approach. Now there may be several causes for the thermal runaway. So studies have determined that thermal runaway reactions occur due to the various reasons, and we have enlisted 4 reasons for this one. Sometimes insufficient understanding of the process chemistry and the energy kinetics of the desired reaction. That means sometimes you may negate the effect of exothermicity. Sometimes it may lead to the improper design of heat transfer capacity required for the plant. Now this is again very important, because you know theoretically that how much quantum of heat being generated in that particular process. So if your design is below the particular heat capacity, then definitely you are approaching towards the thermal runaway aspect. Sometimes insufficient understanding of the adverse reaction and control, including the plant safety backup system as well as the adequate emergency venting. Again, it's a very crucial aspect and attributed to the design of the reactor. Sometimes inadequate written batch procedures and a poor operator training, because sometimes it may approach to this particular reason, and the process condition surpasses this particular critical temperature zone, and if the operator, they are not trained to handle the scenario, then definitely the plant may land in trouble because of the thermal runaway aspect. So never assume a chemical is non-hazardous because of a low hazard rating, and many incidents involve material having having the National Fire Protection Association hazard rating between 0 to 1, but they became the catastrophic in due course of time. So it is best to develop a proper testing program to identify and characterize all reactive materials and reaction mixtures under a variety of process conditions. So that is very much needed, because in Bhopal, there was, it was unlikely that water will meet MIC. And these are very much reactive and created the reaction is exothermic in nature, and the system was not designed at all to cater this type of scenario. So if you are having the hazard rating in between 0 to 1, don't think that this particular system is safe. You have to take the proper measures to safeguard the system. Subsequently, a process hazard analysis that can be used to assign the appropriate control and a safeguard to reduce risk of an adverse event. That is again a very important aspect, because no chemical is non-hazardous. Now it is important to remember to update the process safety information as process undergoes changes during the life cycle. Now the interim process safety information reports can then serve as a reference for the technology transfer purpose as the process scales from research and development aspect, labs, pilot plant to the commercial production stages. Now, once the process has been set, the final process safety report then can be used by the variety of end users, maybe in-house or by outsourced facilities. So, when developing the safety documentation, it is important to keep in mind that it must comply with the company or industry policy and procedures as well as the country and the local regulations, because sometimes based on the gravity of the system, the local authorities or national authorities may impose certain regulations to the thing. So, while designing or while developing all kind of safety related issues, we must know, because certain areas may be designated as a green area, certain may be as an industrial area. So, we must know that what are those regulations, those who are governing and which we need to comply while designing the safety documentation. There are certain things, they are related to the kinetic complications. Now, beware of assuming simple kinetics for autocatalytic reactions, sometimes heterogeneous reaction. Mass transfer may be the rate determining step. Sometimes phase transfer agents may dictate the rate. So, you must know the complexity of the reactions, maybe the multiple steps or in a single step. What are the different routes of those complex reactions? So, these are the various complications, they are associated with the kinetics or chemical kinetics of the process in question. Now, let us have a look about the phi factor. This is a correction factor which is based on the ratio of the total heat capacity of a vessel and the total heat capacity of the vessel contents. So, the phi factor approaches the value of 1 for a large vessels and for extremely light vessels or at a genuine adiabatic conditions. Now, phi factor is usually equivalent to the thermal inertia. Let us have a look about this again, the basic equation A plus B is, they are converting into the product. So, phi factor is designated as phi is equal to 1 plus mass of container into the heat capacity of the container divided by the mass of the sample into heat capacity of the sample. So, it is quite simple. Now, the heat generated in an exothermic reaction is consumed in 3 ways in the usual way: to raise the temperature of the reaction mass, so whatever inside the reactor. Sometimes it is used to raise the temperature of the reactor, and sometimes it may attributed to the heat loss to the environment. So, you may experience that the reactor is having the heat. Now, if phi is greater than 1, then it is considered in the thermodynamic and a kinetic calculation. So, we have enlisted several cases when 1 cubic meter glass lined reactor, then jacket is empty, the phi factor is 1.41, 10 meter cube glass lined reactor when jacket is empty 1.13. 10 gram of Carius tube screening test, that is 2.50, accelerating rate calorimeter 1.50, and then adiabatic pressure Dewar calorimeter 1.05. So, let us think about the testing. This testing should consider the consequences of all conceivable process deviation. This should be conducted under the plant scale heat loss condition or have an appropriate safety factor applied. This should replicate the plant condition in all ways possible, including the use of plant material, consideration of material of plant construction, etc. Now, let us have a look about the rate reaction accumulation, we are not going to devote much time because we are all aware about the accumulation. So this is a condition when the rate of reactant addition is more than the rate of reaction. So you need to plot this dq by dt versus time. So initially you may experience the rapid reaction growth, and then there is a scenario when there may be a chances of slow kinetics. So this is the zone where you can think about the work of a period. Now this is usually determined by the process analysis. I will discuss about the causes not in a very exhaustive manner. Now sometimes you may take the wrong kinetic assumptions, and this may be a very extremely catastrophic, but fortunately in chemical engineering aspect, whatever wrong kinetics we take, it is only just at the design level. So when it is scale up, when it is under the pilot plant study, then we can remove all kind of deficiencies which we have taken at the early stages. Sometimes it may attribute it to the inefficient agitation, because in agitation sometimes the particle may get deposited over the impellers, etc. If you are using those impellers, then the rate of agitation may go on decreasing, and that particular things may be the problematic and attributed to the reaction accumulation. Sometimes the poor temperature control may lead to the reaction accumulation. Sometimes the impurity is attributed to either to reactant, and sometimes the non-intermittent removal of those impurities from the reaction mass may create the problem of reaction accumulation. And sometimes the incorrect initiation may be because of the contaminated raw product, raw material. Sometimes may be attributed to the poor temperature and the pressure control at startup. This may attributed to the reaction accumulation. Now let us have a look about the onset temperature. That is the basic concept. The onset temperature is the temperature at which a reaction can be detected under the prevailing heat loss and the 5-factor condition of the test. So for a given reaction, it is the equipment dependent and not a constant, and normally quoted as a temperature at which the rate of self-heating exceeds a threshold value. So sometimes the knowledge about this particular aspect is essential while designing the safety aspect. Now let us have a look about various safety factors. So safety factors are applied for these runaway reactions to collect data in high 5-factor or high heat loss test equipment. Now 50 to 100 Kelvin for a screen test, 10 to 15 K for the adiabatic test. Now this always apply for a conservative factor to account for kinetic deviation between the reaction types. Now one must beware of autocatalytic reaction or a process with an induction or inhibition period. You may also consider the availability of air while assessing the results. So let us have a preliminary hazard assessment in safety consideration. You need to determine the thermal stability of all reaction component or mixtures within the minimum and maximum process temperature which you can attain under the worst case scenario, because worst case scenario, they are sometimes the deciding factors. You need to identify the unwanted interactions between the reagents and the solvent. Sometimes you need to identify the potential reaction containments that may have an inhibitory or catalytic effect on the desired reactions. Now another is the quantification of desired reactions. So you need to determine the heat of reaction and off gas rates for the desired and quench reaction, including the heat resulting from accumulation of reagent or slow forming intermediates. Sometimes you need to determine the maximum adiabatic temperature for the reaction and determine the basis of safety relative to estimate boiling point of the reaction mixture, and understand the relative rate of all chemical reaction, and sometimes this inclusive of all kind of side unwanted reactions and major reactions, etc. Then you need to go for the quantification of adverse reaction. Now by this way you need to assess the thermal stability of a reaction mixture over a wide temperature range. So while optimizing the robustness of the process Consider other reaction variables such as pH, concentration, conversion rate, off-gas rate, stability of starting and product substrates, etc. in solution or as a slurry, etc. So, you may consider all the probabilities, all the prospects of this particular thing. Then you consider the potential and impact of unwanted vapor phase reactions and develop a chemical interaction matrix for material present in the reaction mixture. Then you need to classify the reactivity and communicate this information to the operational person. So, it has a various step involved for whenever the quantification of these adverse reactions are in question. Then next phase is the plant consideration. Now, you need to conduct a basic energy balance to consider the heat during the various additions, heat generation during the chemical reaction and the heat removal capacity or capability of the plant reactor system. Now, remember to include the reactor agitation as a source of energy, because sometimes we may skip this important aspect while considering this plant consideration. Now, consider the impact of possible deviation from the intended reactant charges and operating conditions. Then you need to identify all heat sources connected to a reaction vessel and assume the maximum possible worst case scenario. Then you determine the effect of lowest possible temperature to which the reactor heat transfer fluid could cool the reaction mixture, maybe that is the coating of heat transfer surfaces, etc. And then consider the impact of temperature gradient and other issues such as increased viscosity, freezing at reactor walls, falling and so on in plant scale equipment. So, in this particular module, we have considered the various aspects of runaway reactions. What is the importance? We discussed about the safety consideration issues, etc. So, if you wish, you can have a look of all these references in this particular slides, those who are given. Thank you very much.